Semiconductor devices. All right, semiconductor devices. We're now moving to an exciting part of the course where we're actually talking about active circuits, things that require power and can do a lot more than what we had with our passive resistors and capacitors. Don't get me wrong, voltage dividers are great. I love them. Filters, awesome. But the real magic in electronics, the real hardcore devices, that happens with semiconductors. Now, semiconductors, such as silicon, are capable of forming really unique devices. In fact, the fact that Silicon Valley is called Silicon Valley is a testament to how useful they actually are. So we're going to talk about some of these devices, but to start with, we're going to have to build up a bit of an intuition on what a semiconductor actually is. So what is a semiconductor? Now, semiconductors are a part of what are called solid state or condensed matter physics. It turns out that's a very big subject. Several courses in your undergrad, graduate school. In fact, it's an active area of research. So we're not going to be able to go too deep into it this course, but we will be able to at least paint a picture to understand how some of these devices are supposed to work in the first place. So a semiconductor. Let's review what we know about the electronic properties of matter to start with. Now, if you recall, we had insulators. Insulators were materials such as rubber that had a set of tightly bound electrons. You could apply a voltage, a large voltage to them, and those electrons aren't budging. In fact, it takes a huge voltage just to get a tiny trickle of current flowing. They have a high resistivity, a low conductivity. Now, on the other hand, we had conductors. What's a conductor? So a conductor has a bunch of electrons that are kind of overall strongly bound to the system, to the chunk of copper or whatever we're using, but they're not bound to any particular atom. Their local potential landscape, as they see it, is very flat, meaning they have no trouble going this way or that. So it's more like a bunch of marbles on a plane, is another way to think about it. And applying a voltage tilts that plane and the marbles or the current flows. But that's not going to happen with an insulator. So how about semiconductors then? Now, a very cool picture emerges when you start looking at these things in these aforementioned hardcore solid-state physics courses and condensed matter courses. We look at the electrons in terms of how much energy they have versus how much energy there is pulling them in place. So a very cool and useful picture emerges when we talk about condensed matter physics in terms of the allowable energies and the energies required for the charges, to move around on the lattice. In this picture, we talk about the bands or the electronic band structure. So the energy of the electrons as they sit in their lattice, their local set of atoms, is called the valence band. That's the energy they're occupied. And we can also talk about the conduction band, the next level of energies that would correspond to zipping around and forming a current and being free. So an insulator has a large band gap. If we see this, there's a band gap, a range of energies, a gap of energies rather, between where the electrons currently are and where they need to be to conduct. In a conductor, in fact, the band gap is not only small, it's vanished. So the electrons already have enough energy to zip around here. And in a semiconductor, it turns out that band is just very small. That's one of the properties of a semiconductor that unfortunately we're not going to be able to go too deep into. Although if we were developing and learning how to build our own semiconductor devices, we'd really need to focus in on the band structure of condensed matter physics. So we're going to build an intermediate picture of how these things work. And we're going to attack it by looking at kind of three levels or three properties of semiconductors that make them useful. Note that it is not the case that an insulator has such and such a resistance, a conductor has a much lower resistance, and a semiconductor is in between. That would not be useful, would not be worth talking about. It's actually that we can apply external factors to these semiconductors and change whether or not they behave like a conductor or an insulator. And it's this engineering of its electronic properties that really make semiconductors almost magical devices. And we're going to attack this in three steps. So let's look at the first thing about a semiconductor. It's atomic structure, namely how covalent bonds are formed. So our prototypical semiconductor is silicon. Let's look at where silicon is in the periodic table. We see that it has 4 valence electrons. There's 8 possible slots in that shell to fill, so it's halfway filled. It's got some room as it sits there on its own for extra electrons. And that allows it to form a special type of bond with other silicon atoms called a covalent bond. And this is the picture of a covalent bond. So each atom here, each silicon atom, has 4 neighbors, and each pair of atoms shares an electron. That way, every silicon atom has a filled shell of electrons. Everybody's really happy, and they're all kind of bound this way in this crystalline structure. So I have to admit, before we go too far into this, that this is a cartoon picture. What is a semiconductor? It's not a piece of paper, it's a chunk, it's a crystal. You can have a silicon crystal, it's 3-dimensional. So it does not look like a plane like this, but this helps us understand how it works. In fact, if we actually look at a picture of a model of how it works, this is the crystalline structure of silicon. It's 3-dimensional, and if we drew this, if we imagine this thing just repeating itself and repeating itself and repeating itself, that's what silicon looks like. However, it would be very difficult to analyze. In this structure, it turns out there's 4 nearest neighbors, and that's precisely what we've been drawing with this kind of cartoonish picture here. This picture captures all the physics of this mess here. So we're just going to stick to this. Now, something you might notice right off the bat is that if all the electrons are in their cozy homes here, they're not moving around. That describes a perfect insulator. In fact, you'd be 100% right to assume that if everything was completely static. If, however, I could reach in there and flick a few electrons off, those electrons would just be zipping. If I could flick them hard enough such that it's harder than the force that's holding them in there, they'd be zipping around the lattice until they find another slot that was left by another flicked electron. But how hard do I have to flick it? Well, it has to do with the binding energy of the electrons here. And it turns out for silicon, it has to do with that band gap. It's fairly small. It's about 1.1 electron volts in the case of silicon. So that means I only have to flick it that hard in order to release an electron. So if I overcome that, we can get free electrons and therefore a current. Now, of course, I can't go in there and manually flick all the electrons off. That might be challenging, but we can allow nature to do it. We can apply a little heat. And if we heat something up, what is temperature? Temperature is just thermal energy, which corresponds to, in the case of a solid, vibrational energy. So the higher the temperature gets, the more vigorously and crazily these atoms are all zipping around and bumping into each other. It doesn't take much temperature before they have enough energy to be completely bashed free from one another. Now, it turns out this thermal energy, you can actually calculate it. Even at room temperature, it's much less than 1.1 electron volts. It turns out it's about 0.025 or about 1/40th of an electron volt. But that's a distribution. There's still a tail to that distribution, and there's enough atoms that happen to have more than 1.1 electron volts of energy to form a reasonable current, a reasonable conductivity through the silicon. Now, if we go down to absolute zero, in fact, even if we're at liquid nitrogen temperatures, there's like no conductivity. There's essentially no probability that an electron, or rather an atom, will have enough energy to wiggle itself. But even at room temperature, we start getting a conductivity. Now, it gets more and more and more, and eventually it'll be insanely high as the temperature increases. So the first point I want to make is a semiconductor is, because of its structure, it's a perfect insulator at 0 Kelvin, and as the temperature increases, you get more and more free charges that can form a current. Your conductivity is going to increase. And this mechanism is called intrinsic conduction. Okay, so that's quite neat. We can tune the temperature, but it's not that neat. It's not worth having a valley in California named after you. It's not going to cause a technological revolution. But luckily there's more. We can exploit the atomic structure of the semiconductor in such a way to perform some very neat technological feats. Okay, so let's look at the next thing we can do called doping. We can take a similar atom on the periodic table, for example boron or phosphorus, and we can place it in the lattice. It's going to fit nicely in there, but it will not have the same number of electrons. So if we look here, we have, for example, boron that is trivalent. It has 3 extra electrons in its outermost shell. Now, it's not going to be able to form nice covalent bonds in the same way that silicon is, such that every shell is filled, but you can put 1 in every million silicon atoms, no problem. Throw a boron in there, and it's going to fit nicely and snugly into the lattice. Although it has fewer electrons, it'll fit in there. Similarly, phosphorus here has 5 electrons in the outermost shell, so it's going to fit nicely into the atomic lattice as well with this extra electron. That extra electron, or that lack of an extra electron, is going to be all the difference in the world. So let's look at what we get when we do that. Let's take one of these phosphorus atoms and we'll shove it into a silicon lattice and see what we get. Now it has 5 outermost electrons, but it's roughly the same kind of shape, if you will, of atom. It can fit into that lattice nice and snugly, but it's going to have that extra electron kicking around. Sad little electron there, and doesn't have a partner to covalent bond with, so it's just going to be floating around. But because all the partners are spoken for, and because we're going to have this thermal agitation moving things around, that poor little electron is going to get blasted even further from their home. It just gets sadder the more I say this out loud, but this electron is going to be zipping along the lattice. It's not particularly bound to any particular atom because it sees a fairly flat potential. When it does this, it leaves behind a positive ion where its parent phosphorus was. So this, every single phosphorus we put in there leads to an extra electron, a negative charge that can be added to the current. And if we apply an electric field, that's just going to get swept away. So for that reason, phosphorus and pentavalent semiconductor dopants form what are called N-type or negative type semiconductors. Well, now let's do something else. Let's put a boron atom in here, or an aluminum, or any group 3 atom that is trivalent. A similar picture emerges, but now instead of a pentavalent, we have a trivalent electron in there. It has one too few electrons, and now there's an extra slot for the electrons to snuggle into. So they have no problem hopping over into that boron slot there. And as they do so, because of thermal agitation bumps them, they find themselves in a new local potential minimum, and they're happy staying there until they get knocked out again. And when they do hop over, they're going to leave behind, well, a positively charged hole in the silicon atom that they came from. So instead of the hole in the boron, you have it in the silicon. And in this way, we can actually look at the propagation of holes as quasi-particles that behave just like positively charged electrons. It's a bit weird until you see that. So let's kind of picture one of these processes here. So here we have a hole up top, and it's going to leap over to its neighbor. In fact, the hole isn't leaping over, the electron is leaping over next to it. And then the electron next to that one is leaping over, and the next one, and the next one. But if you stand back and look at it, it looks as if there's a positively charged particle moving to the left, but really it's just a cascade of electrons moving to the right. And as the different neighbors hop from hole to hole, and you can track where that hole is, although it's only electrons that are moving around, it looks exactly as if you have a positively charged electron moving around. So there's 2 types of charge carriers that we consider in semiconductors, electrons and holes. And because the holes are positively charged, we say that when we dope a semiconductor with a trivalent group 3 atom like this, impurity, we form a p-type semiconductor, positive type semiconductor. So that's quite neat. The charges from the donors are called the majority charges. So in p-type it's holes, n-type it's electrons. But in the background, this thermal stuff with silicon is always going around. And it's not going to be dominant under most circumstances unless it's really, really hot. So we call those the minority charge carriers. So kind of a picture of what's going on so far is we start at like 0 Kelvin. Nothing can move, not even the holes in the electrons. 1 Kelvin, 2 Kelvin, same thing. There's just not enough thermal energy to shake even the electrons in the holes free from their boron or phosphorus atoms, whatever we're using. But it doesn't take much. So at very, very, very low temperatures, even a doped semiconductor, P or N-type, is a perfect insulator. As we start cranking up the temperature, we'll start seeing some interesting stuff. So here's a graph of that process. Near 0 Kelvin, we have near 0 conductivity. And what we're actually looking at here is the free charge density, the density of these charge carriers. So at low temperatures, we call that the freeze-out region. The freeze-out region, everything's frozen out, nothing can move. And then we increase the temperature, and all of a sudden, very abruptly, we get overcome that barrier, because it doesn't take much for the barrier to be overcome for the majority carriers, the holes in the electrons. And the conductivity just shoots up. But then it flattens out. Why does it flatten out? Well, there's only so many boron, there's only so many phosphorus atoms that we're putting in here. It'll flatten out when they're all participating in conduction. And then it should just go on forever. When we do this is called the extrinsic region, right? When we had the thermal agitation that caused the silicon to knock a few electrons free, that was intrinsic conduction. When we do it with the dopants, that's called extrinsic conduction. So we have this extrinsic region here. And then the thermal catches up, right? It just skyrockets. When that happens, we have enough temperature. We're just knocking so many electrons free from that temperature that that even overwhelms the electrons and holes from the dopants. All right? There's only a fixed number of them. And eventually, we jostle the silicon lattice enough, we're going to get more electrons from the lattice itself. And we're going to concentrate, all the devices that we're interested in are going to concentrate in this region here. Okay, and that's how we're going to make some neat stuff. Okay, so where are we? We have maybe not a technological revolution level of technology, but we have some cool stuff. With industrial processes, we can dope a certain amount of a certain density into a silicon lattice and arbitrarily tune how many charges we get per unit volume. We can tune our charge density. That's pretty awesome. That leads to some neat stuff. Still not enough though for a valley to be named after you. That will happen when we take a p-type and an n-type and shove them together. The interface of a p-type and an n-type semiconductor, that's where the magic really happens. So let's actually figure out why this is. Now suppose that I take a glass of water at some temperature and drop a bit of food coloring inside. Now over time, well, the color is going to spread out, a process known as diffusion. Note that there's actually real atoms being knocked around here. It really is on some level due to forces banging and bashing into these atoms to distribute them. After a while, the color is equally distributed, neglecting density variations and things like that, and maybe the red part will be on the top, but it's going to be fairly uniform. Does this mean the diffusion is stopped? Not really. It's still going on, but on average, everything is perfectly mixed and everything is together. It's still going on in the background, and the same is happening inside a semiconductor. When we have a intrinsically positive semiconductor, p-type semiconductor, we're going to have holes that are just diffusing around all the time. In an n-type, there's electrons which are zipping around this thing, and they're all kind of meandering in their own way due to these thermal agitations, being bashed from the left and the right and up and down. So that's happening all the time, and that's a key to what's interesting about this. So we'll take this p-type and this n-type here, and inside this thing, we're going to have this diffusion process going on. So let's make a perfectly smooth interface. We'll make them very flat and we'll shove them together and form a junction here, a p-n junction. So this diffusion is still going on. What does this look like? For us, we can see, oh, there's a p-type and an n-type. But for the electrons, what do they see? Now, the doping concentrations are very weak. Like heavily doping is like 1 for every million or something like that. I should look up the actual number. But there's even if you're heavily doped, even if you put a lot of boron into your silicon, it's mostly silicon. An impurity moves around and it sees silicon everywhere, silicon up, left, down, right, center. Occasionally it runs into a donor atom, but it's almost always silicon. Therefore, the smooth boundary, it doesn't know that it went from a p to an n-type or vice versa. It just it saw silicon before and it sees silicon after. So it's just swimming in silicon. So it's just going to diffuse over on its own. But note that if it did this, there was one, for example, electron that was before on one side and after on the other side. So we have a small net charge building up. And as more and more diffusion happens, back and forth, a larger and larger charge imbalance will build up, right? As more and more electrons diffuse over, they're going to leave a net positive charge. As more and more holes will diffuse over, they'll leave a net negative charge on the other side. And this will continue. It won't go forever. It's going to continue until there's a Coulomb force, a barrier, just due to the F equals QE. We all know from electromagnetism. There's a force associated with that charge distribution. So they'll get pulled back. Now remember, there's two forces going on here. There's the charge force, and then there's the bashing and banging of the atoms. So this is going to balance itself out. And it's going to lead to a distribution when there's enough charge to just balance out all the hammering on one side of the atoms that are thermally agitated. And this will lead to this picture where we have negative charge on one side, positive charge on the other side. But this is very cool, because if we have a charge distribution, that means we have an electric field. And if we have an electric field, we have a potential difference. We have an energy per unit charge. So we've actually just made a voltage source, not by making a battery, but literally by taking one type of doped silicon with another type, banging it together. That's it. That's our junction. It creates a voltage source. So it's like tempting to think there's a battery in here. There's a potential barrier in this thing, right? And there's two processes going on, remember. There's the diffusion, just from the thermal agitation, and the drift of the charges that are being pushed by this distribution. And in equilibrium, they balance out. So the first time I heard this, I thought, great, perpetual motion machine, awesome. We're all getting rich. Unfortunately, it doesn't really work out. So let's find out why. It's a little bit subtle. Let's make a perpetual motion machine. I'm going to wire both ends of this thing together and draw current. Maybe I'll put a little inductor down here, and I'll just sit and collect the joules. And I get free energy, right? There's a subtlety, though. Unfortunately, sadly, it doesn't work out that way. Because you can form a p-n junction between a p-type and an n-type, but you can also form a junction by the same arguments from a n-type and a conductor, or a p-type and a conductor. And it turns out that we've just formed two such junctions wherever we've hooked up the wires. And it turns out, annoyingly, no matter where you do it, so here's the two junctions here, no matter where you do it, if you kind of evenly taper off the amount of doping from one side to the other, it's always going to balance out. Mathematically, it will always work out such that the p-n junction in the middle is balanced by the other junction you've made, and you get no net current one way or the other, therefore no perpetual motion machine. Okay, so no free lunch, but we can still do something very neat. We can pay for our lunch with a battery here. Let's shove a battery there and plug it across the terminals, and we'll put it in such a way to balance out, or try to balance out, the barrier drop, the barrier potential that's inside this diode. And initially when we start cranking up the battery, we start raising the potential of those electrons there, such that there's still a harder push one way versus the other, but it's getting smaller. That gap is getting smaller, right? We're just raising the potential of one side. And if we keep doing that, if we keep cranking up the voltage, so to speak, well, eventually we're going to overcome that barrier, and we have current flowing now. So we've actually made a device which is like a perfect resistor up into a point, and then it turns into a wire, an open circuit to a closed circuit. And this is great. We've actually made a one-way barrier for current. What if we went the other way? Now, if we put the battery the other way, we're actually just lowering the potential on this right side here. And this is only going to further the barrier. No current's going to flow when we turn it around the other way either. So what we've actually done here is we've made something called a diode, a one-way valve for current. As long as we're over this barrier voltage, the diode drop voltage, as we'll call it, we actually get current flowing. And below it, we get nothing. This is a nonlinear device. It doesn't obey Ohm's law. We don't double the current. We don't double the voltage and get double the current. We either get, it's kind of all or nothing in this model. So this is great. I should just say one thing finally as we're nearing the end here. It's not actually all or nothing. There's a slight transition period, and that transition is called, described by the Shockley Equation. I joke you not, one of the people that worked on this and invented the transistor was named Shockley, but history has its ironies. So this is the Shockley Equation here. It tells you the current versus voltage characteristic. Remember, with Ohm's law, we looked at the current versus voltage for resistors. We can do the same thing here, make an IV curve of the diode, and it's governed by this equation here. Now there's a few squiggles. So we have this reverse saturation current. It's a very small number, nanoamp or something like that. And we also have here on this exponential term, so it's an exponential increase. It'll change very quickly. On the numerator, we have the electronic energy. In the denominator, we have the thermal energy. So it's kind of a neat way to wrap everything up. And if we actually plot what that looks like, well, it's not quite an abrupt change, but it's fairly abrupt. It changes very quickly. It becomes very steep. So a current, voltage versus current, I over V is the slope. That's 1 over R. The slope is like infinity very quickly. So the resistance goes to 0. for anything well over the diode drop voltage, and the resistance goes to infinity. There's like no current that flows no matter how hard we push it the other way. And this is the IV characteristic of a diode. And we're going to now put on our 229 hats. Now that we've understood the physics, at the atomic level, we've understood how these devices work. We're now just going to put them in an abstract model in a black box, or a white triangle here, and we're going to forget about the guts of it, how it's made. But we can always go back to it to understand it and understand the nuances more. So next lecture, we've all done a lot of work today. I think we all need a break. But next lecture, we're going to talk about how to model these things in a simple circuit, and how to actually make useful things out of them. That'll be next time.